Hello. So in this relatively short section, Haberman's section 2.2, we'll talk a little about kind of what linear operators are in general, because kind of, so when we solve the heat equation, right, that piece, that Laplacian, turns out to be linear. And so what we want to do is be able to talk about kind of how we can mix and match solutions that we get to kind of the Laplacian and some of these other differential operators, and just get a very general sense of, right, how we can combine these solutions, which is going to be important for when we start constructing series solutions and these things called Fourier series. So in this section, we'll talk a little about, you might say, more of the general theory for linear operators. Much of this should be some sort of review from a previous linear algebra course, but focused on kind of differential operators and how they are linear. Okay, so the two main kind of things we'll talk about are, right, what are linear operators in general, after which we'll talk about this principle called superposition, which lets us combine solutions to certain kind of linear equations to get new solutions. So linear operators, right? What is kind of a linear operator? So an operator L is linear if, when you apply it to kind of a linear combination of two vectors, V and W, where A is some scalar, then we say L is linear if, in a sense, this distributes across kind of addition of vectors. And moreover, if you have kind of L applied to AV, right, so let me write it over here, LAV, then what we can do is pull that scalar out to get A times LV. And so kind of implicit in a lot of what's written here is, right, that, right, well, V and W are vectors, but L is something so that if you plug in a vector, you're going to get out another vector, right? So this is a vector, we're applying L to it. On this other side, L applied to V, this is some vector, and then we're scaling it by A, okay? Kind of the vectors and linear operators that you're probably familiar with are, you know, vectors of numbers, and the linear operators are matrices generally, but, right, kind of this definition and this whole framework works in general. It doesn't matter kind of what the specific vectors are and what the specific linear or operators are. It's just that operator is linear if this equation is satisfied. Okay. Yeah, and so kind of the vectors that we'll focus on most are going to be functions, scalars. The scalars are still going to be real or complex numbers, but now the differential or the linear operators, well, okay, the operators we're interested in are differential operators, and what we'll see is that, right, indeed, differential operators applied to functions as vectors, you know, everything works out. Right, apply a differential operator to a function, you're going to get a new function. It's an operator. Okay, so what are some kind of specific examples of some of these operators that we're particularly interested in? So one example is going to be what we're going to call the heat operator, right? And so this is defined as, right, so this is the name we're giving this operator. What is this operator? Well, apply one time derivative and then subtract k times two spatial derivatives, and that's the operator. Okay, so if you apply this operator L to a function u, what does this look like? Well, we're applying this derivative minus k d squared dx squared. We're applying all of this to a function u. Okay. So, right, well, how do we evaluate this? Let's distribute u across there. We're going to get du dt minus k d squared u dx squared. And that's how this operator L acts on vectors u. Okay. And then this is the vector that gets output. Okay. And so, right, why do we care about this? Well, right, solutions to the heat equation, which are kind of some of the things that we're interested in. Those are vectors u that satisfy this, right? L applied to u is equal to 0. And of course, if you actually write out what you have, right, this whole thing equal to 0, move this to the other side, you get the heat equation that we've been studying. So that's one example. Another example is what we'll call the wave operator, or sometimes in physics and other literature, you'll see it called the D'Alembert. I don't know, we'll call it the wave operator. And of course, what is the action of this? Well, L applied to u, what does that do? It says we take 2 time derivatives, and then we subtract c squared times 2 spatial derivatives, all of that applied to a vector u. And then what does this actually do? Well, say distribute this, or kind of have both of the derivatives applied to it. You're going to end up with d squared u, t squared minus c squared, d squared u, dx squared. Okay. And so solutions to the wave equation, right, those are things for which LU is equal to 0. And then you can, right, compare that to the form that we've seen before by just, right, moving this to the other side, and you have the ordinary wave equation. Okay. So these are two kind of specific linear operators that we care about in this course. Okay, and so, right, one question is, well, why are these linear? Kind of what's the verification in that? And so that's something that we can check, right? So here, right, u and v are functions. They're as differentiable in both t and x as we need them to be. A is a scalar, can be real or complex. In this case, it doesn't really matter. And so then, right, to verify that this operator L is linear, we need to show is that, well, if you take L and you apply it to this linear combination AU plus V, what you want to end up with is A times L applied to U plus L applied to V, right? So I'll write it here. So LU plus LV. This is what we want. Okay. Okay, so how do we verify that? Well, let's just go through kind of, right, what we can do. So, right, we're applying this operator, this heat operator L, to this linear combination AU plus V. And so, right, what does the heat operator do? Well, take whatever function you have, in this case, AU plus V, take one time derivative, and then subtract k times 2 spatial derivatives, right? So this right here, or I should say this equality is by definition of what this operator L is doing. Okay, great. And so now what we can do is we can say, well, right, sure, this is what L is doing, but let's look at the pieces. So here, right, we're taking one time derivative, okay? And when we take derivatives, right, that operation is linear. Should say, so like recall d dt of, all right, AU plus V, right? This is going to be, right, so the derivative of a sum of functions is a sum of derivatives. d dt of AU plus d dt of V. Okay. And then if you take the derivative of a constant times a function, that's equal to the constant times the derivative of the function. So this scalar A, this we can also pull out. So we get A d dt u, actually let me write it like this, du dt plus dv dt. Okay. So what that tells us is that this expression right here is equal to this, right? In a sense, by linearity of kind of the first derivative for one of the variables. Same exact reasoning can be used to show that, right, if we have two derivatives, right, that operation is linear as well. So these two derivatives, they distribute over the sum, and then we have a constant a times a function. So if we take two derivatives of the constant times a function, that's equal to, right, the constant times two derivatives of the function. And so all of that is why this is equal to this whole thing right here. Okay. And so keep in mind right here, we have a sum in here, but then we're distributing this minus sign to each of those pieces. Okay. So what we've done is, right, take this expression that we care about, write out the definition of it, and then use linearity of two of the pieces to essentially just write out all of this stuff. Okay. And so now what we're going to do is we're going to collect terms, right? So this piece is an A in front, this piece is an A in front. So let's factor out an A, right? And then what we end up with is this. Okay, but then the observation is that, oh, this piece right here, this is exactly L applied to U. Right. And then similarly, right, everything else that's left over, this whole thing right here is exactly L applied to V. So what we end up from this line is, right, we have A multiplied by L applied to U, so it's that, plus L applied to V, which is that. Okay. And that's exactly the expression we wanted, right? So indeed, this heat operator L is linear because take L, apply it to a linear combination of these functions, and you get that linear combination of kind of L applied to the functions. Okay. And so, yeah, I guess the note is that linearity for this heat operator really comes down to linearity of just like derivatives, which is something, right, we're already comfortable with, we use all the time. So all we're doing is kind of piecing things together and then right, saying these observations using a slightly different language. But takeaway is that yes, the heat operator is linear. And that boils down to, right, the actual pieces of this heat operator, they themselves are linear. Okay. And you can do the same thing to show that the wave equation or the wave operator is also linear. Cool. Okay. So what is a linear equation then? So kind of the definition we'll take is, right, so a linear equation for some unknown vector u is any equation of the form LU is equal to F, where L is a linear operator and F is some vector that we're given. Okay. Right, so the form that we kind of, how do I say this? Linear equations that kind of we see all the time might look like AX is equal to B, or you might have a system of equations that look like AX plus BY is equal to E, and then CX plus dy is equal to f, right? So both of these, right, can be written in this form. Ax equals b, right? Well, that's kind of given. But the question is, well, how's this thing written as a linear equation? Of course, if we write out A, B, C, D, this matrix applied to the vector xy is equal to EF. So now this is a linear operator because it's a matrix. This is our unknown vector. And this is a given vector. So, right, this system of equations is in fact a linear equation. Okay, so a linear equation is just anything, any equation in this form where L is a linear operator and F is a given vector. Okay, heat equation with non-zero source. Right, so that looks like du dt is equal to k d squared u dx squared plus q. Well, we can rewrite this as du dt minus k d squared u dx squared is equal to q. And of course, this is Lu is equal to q, where L is the heat operator and then q is the source term. Okay, so the heat equation with the source is indeed a linear equation as well. So if kind of this vector on the other side, if this vector f turns out to be 0, and so then we're solving the linear equation, right? Lu is equal to 0. Those are special enough that we call them homogeneous. Okay, but that's a special case of a general linear equation. Cool. Okay, so all of this is kind of language to talk about kind of the sort of equations that we're interested in solving in general. And so the question is, well, great, so what are we going to do with all this stuff? The main thing that we're going to need for everything is this principle called superposition. Okay, and basically it says if you have, say, 2 solutions or however many solutions to a homogeneous linear equation, then you can add those solutions together and get a new solution. Okay, which isn't necessarily true, or which isn't true if you have kind of a non-homogeneous equation. Okay, but we're going to use this kind of here shortly to essentially construct solutions to the heat and wave equation in general. Okay, so the observation that I just said is that, well, if you have two vectors that satisfy kind of the same linear homogeneous equation, then if you take any linear combination of those, that linear combination also solves the same equation, right? So the fact that U1 and U2 they solve a linear homogeneous equation, that's what this statement is, right? L applied to U1 is equal to 0. Likewise, L applied to U2 is equal to 0. With L here, L is linear. Okay, so if L1 or L applied to U1 is 0, L applied to U2 is 0, and then here the other assumption is that C1 and C2 are scalars. Okay, well, so the question is, right, what about this linear combination of U1 and U2? So let's look at what happens if we apply L to this linear combination, right? So if L is linear, okay, we can distribute it across the sum. So let me fill in the blanks here. So L applied to C1, U1 plus C2, U2. This is equal to L applied to C1, U1 plus L applied to C2, U2. Okay, so great. C1 is a scalar and L is linear, which means we can pull the scalar out. Likewise, C2 is a scalar and L is linear. So this scalar can get pulled out. So this is equal to C1, L applied to U1 plus C2, L applied to U2. Okay. But the observation now, so right, this is exactly that. Okay. So the observation here is that, well, U1 and U2 are both solutions to this linear homogeneous equation, right? Which in practice means this thing right here is equal to 0. Likewise, this thing right here is equal to 0 from that. So we get C1 times 0 plus C2 times 0, which of course is 0. Okay, so L applied to this linear combination is also 0. Okay, so again, the conclusion is that, well, if U1 and U2 satisfy this linear homogeneous equation, then any linear combination of the two also satisfies the same linear homogeneous equation, right? Or in other words, if we have two solutions, we can add them up and get another viable solution. Cool. Great. So, great. So for us, this is important because, right, the things that we'll be solving are going to be linear homogeneous PDEs. Okay. So, right, L, U1, U2, kind of from the previous slide, L is going to be something like the heat operator, and then U1 and U2 are going to be functions that solve, heat operator applied to something is equal to 0. Okay, and so this is something that we'll see explicitly written out here shortly. Right, and so kind of the other comment to make is that this kind of homogeneity, right, should hold no matter where you evaluate your function. Okay, and so in particular, it should also hold at the boundary, right, for whatever boundary conditions you use. So kind of the statement here is that, well, right, we were talking about boundary kind of linear equations and kind of the form they have to take to kind of be a linear equation. Right, and so right, so linear equation, LU is equal to F, where this is a linear operator. And then F is going to be, this is a given vector. Okay. Right, and so this kind of framework, we can also speak about or kind of use this language for boundary conditions. So, right, boundary conditions can be linear, they can also be homogeneous, they can be one or the other, or they can be neither, right? Although I should comment, so generally if we say something is homogeneous, it means it's linear and then it's also homogeneous. So if we have a nonlinear thing, we don't necessarily speak of it as being homogeneous. But anyways, right, so we've seen a bunch of possible boundary conditions, right? So like for one example is specify the value of a function at an endpoint. This is linear, but non-homogeneous. Okay, we can also specify the derivative at one or the other endpoint. In this case, this one is linear, also non-homogeneous. Now as a special case, right? So here, where we're specifying the value of the derivative, and what that has to be is 0. So this certainly is a linear equation. In this case, though, this one is homogeneous. Okay. We also saw that we could kind of mix and match and have, right, these linear combinations of bound or of kind of derivative and the function value. And so this one, I believe it was written kind of in a form like this previously, but we can rewrite this as, let me find the right. So this we can write as h times u of lt plus k0 du dx of lt. That is equal to h g of t. This is linear and it's non-homogeneous. Okay. One way to see it's linear is to, well, write it as a linear operator times a vector and have that equal to another vector. And we can do that by writing this as the vector h k0 multiplied by the vector u of lt and then du dx at lt, and have this equal to the one-dimensional vector h times gt. So here, this is a matrix. Okay, that's our linear operator. This is our vector, and this is our given vector. So indeed, this, we can write it quite explicitly as a linear equation. If g of t is not necessarily 0, then this won't be homogeneous, but it definitely is linear. Okay. So in the final one, this one is nonlinear. And the main reason is, right, we have a product, kind of this nonlinear operator of the solution that we care about. Okay, and so we'll see. So yeah, so that's it for this. So kind of in the next section, we'll actually see this used. And again, the main thing is, right, we'll be looking at kind of the heat equation with homogeneous boundary conditions and no source. And so what kind of how we'll get at solving that is we'll kind of construct a bunch of solutions or find a bunch of solutions to the heat equation. Use the fact that it's a linear, kind of a linear homogeneous equation, and then kind of use this principle of superposition to add all of these solutions that we find together to get another more general solution. Okay. So that's what you can expect coming up.